Hello dear students and welcome back to the discussion NCERT line by line questions. Today we discuss one of the most important chapters, the current electricity. Okay, without wasting much time, we enter into the questions. The first question, estimate the average drift speed of conduction electrons in a conductor of cross-sectional area 10 power minus 7 meter square carrying current of 1.5 ampere. The number density of conduction electron is 8.5 into 10 power 28 per meter cube. Average drift speed is asked. Average drift speed VD. How much is the drift speed is asked. The cross-sectional area of the conductor is given in the question 10 power minus 7 meter square. Okay. The current passing through the conductor is given I is equal to 1.5 ampere. Okay. The number density of the electrons, that is the number of free electrons per unit volume of the conductor, N is equal to 8.5 into 10 power 28 per meter cube. Okay. So very direct question. We have the relation connecting current and drift speed as current I is equal to NEAVD. Electric current passing through a conductor is equal to number density, electronic charge, area of cross section of the conductor, then drift speed of the electrons. From this, VD is equal to I divided by NEA. Okay, very direct calculations. Current is 1.5 divided by number density 8.5 into 10 power 28. Electronic charge 1.6 into 10 power minus 19. Cross-sectional area of the conductor is 10 power minus 7. Okay. This is equal to. First of all, we calculate the power of 10. 10 power 28 into 10 power minus 19. Okay. This is equal to 10 power 9. Right. Yes. 10 power 9 into 10 power minus 7 is 10 power 2. Okay, to the numerator it is 10 power minus 2. Okay, then 1.5 divided by 8.5 into 1.6 into here 10 power minus 2 in the numerator. Clear? Yes. See, 1.5 divided by 8.5. This is 15 divided by 85. Okay, 15 divided by 85, that is 3 divided by, we can write, we can divide with 5. 15 divided by 85. We can divide with 5. 3 divided by 17 into 1.6 into 10 power minus 2. Okay. If we take one more 10 here, then this will be 10 power minus 3. Then 30 divided by 17 into 1.6. 17 into 1.6, nearly 28 in that range. Then 30 divided by 28 is, see, just greater than 1. And here the power will be 10 power minus 3. Then that is milli. Okay. Now here the answer is 1.1 millimeter per second. Okay, 1.1 millimeter per second. This is a direct question, okay, which deal with the relation between electric current and drift speed of the electron. Clear? Okay. The next question. Average collision time for electrons in a conductor under a certain potential difference is found to be 10 power minus 15 seconds. Okay, the time between the collision, the average time, that is the relaxation time. The relaxation time is represented as tau. Okay, tau is given as 10 power minus 15 second in a particular conductor. Okay, the mobility of the electron in the metal conductor is asked. Mobility, you know, mu. Mobility mu is defined as the drift speed VD divided by the value of electric field intensity in the conductor. The ratio of drift speed to the electric field intensity is called mobility. Okay? Yes. Now we have the equation of drift speed as see, drift speed Vd is equal to E divided by m into tau. This is a basic equation connecting drift speed, field intensity and relaxation time. Clear? This is the equation V is equal to u plus at. Here u is 0. Acceleration is force by mass. Force is charge into field intensity. Charge into field intensity is the force. Force by mass is acceleration. Acceleration into time. This is the final speed. Okay. This is how we derive this formula. Clear? Now in this expression, what will be Vd by E? Okay. Vd by E, Vd by E will be is equal to E by m into tau. Right? Yes. E by m into tau. And this is what mobility. Mobility now it is E by m into tau. Okay. E by m is the charge to mass ratio of the electron. Electronic charge divided by electronic mass. It is the charge to mass ratio of the electron. And it is a constant. We have to study it as. Actually, this is 1.6 into 10 power minus 19 divided by 9.1 into 10 power minus 31. We get 1.76 into 10 power 11. Okay. Now into, okay, you just by heart this E by m. That is the charge to mass ratio of the electron is 1.76 into 10 power 11 into tau is given in the question as 10 power minus 15. Okay, this is the answer. Okay, 1.76 into 10 power minus 4. This is the mobility. Okay, its SI unit is velocity divided by field intensity. Velocity meter per second. Field intensity is Newton per coulomb. Okay, Newton per coulomb or volt per meter. Newton per coulomb or volt per meter. So it will be meter square per volt per second. This is the SI unit given here in the option. So the answer is 1.75 into 10 raised to minus 4, or approximately this is approximate result 1.76. Okay, so this is the answer given in the option. Clear? Okay, the next question is, a charged particle is having drift velocity of 7.5 into 10 raised to minus 4 meter per second in an electric field of 3 into 10 power minus 9 volt per meter. Okay, the electron mobility is a very direct question asking the mobility mu. Equation is Vd divided by field intensity. Direct calculation. The drift velocity given as 7.5 into 10 power minus 4 meter per second divided by the field intensity given 3 into 10 power minus 9 volt per meter. Okay. Yes. 7.5 divided by 3 is 2.5. Clear? Into 10 power minus 4 divided by 10 power minus 9. 10 power minus 4 cut. And here remains 10 power minus 5 to the numerator. It will be 10 raised to 5. Okay. And the SI unit is meter square per volt per second. Okay. Yes. 2.5 into 10 raised to 5 answer is option B. Understood? Very direct question. Okay. The next question is, arrange following materials in the correct order of their conductivity. Okay, nichrome, copper, germanium and silver. Okay, out of this, the conductivity is more for silver. Okay, after it is copper. Okay, then germanium, semiconductor. Finally, an insulator, that is the nichrome. Okay, so the greatest conductivity is for silver, then copper, then germanium, then nichrome. This is the answer, option B. Very easy question, right? Okay. The next one, number 5. The resistivity of alloy manganese. Manganese is a material we use it to select to build or to construct the resistance wires. Because manganese has least dependence on temperature. Manganese, the resistivity of manganese is almost a constant with the temperature. Okay, so it is nearly independent of temperature. That's why it is used as a resistance wire. manganese, constantan, etc. There are certain materials which are used as resistance wires, because as temperature increases, the resistivity is not at all increasing and remains as a constant. That's why. So this is the answer, option D. Okay, option D. Clear? Okay. The next question, sixth one, is a graph. The graph of resistivity versus temperature for copper is best represented by the graph shown below. The correct graph is, see, in the case of copper, as temperature increases, the resistivity gradually increases. Okay, the resistivity gradually increases. And that increment is not linear. It is not linear. That's the point. Okay, at a higher temperature, the resistivity increases more, in more rate. Okay, so we studied the graph, this one. This is the graph. Clear? See, initially, see, this is temperature and this is resistivity. Okay, initially as temperature increases, resistivity also increases. But this rate is not constant, the slope is not constant. Later, as temperature is in the greater range, resistivity increases more in that way. Okay, this is how the variation we studied. Okay, yes. The next question is, a resistor is marked with rings colored as brown, black, green and gold. Okay, the first two colors are the digits and the third color indicating the multiplier of 10, the fourth color indicating the tolerance that we studied. Okay, here the colors are brown indicating 1, right? Then black indicating 0 and green indicating 5. Gold is the tolerance which indicating 5%. Right? We have studied the shortcut B. Roy of Great Britain has a very good wife. Okay, in that way. Black 0, brown 1, red 2, orange 3, yellow 4, green 5. Okay, green is there. Right? Okay. Then the resistance will be R is equal to, first color is brown, that is 1. Second color black, that indicating 0, into 10 to the power green is 5. Then plus or minus the tolerance is gold, indicated by gold, it is 5%. Okay, then what's the answer finally? 10 into 10 power 5 is 10 power 6. Yes, 10 power 6 plus or minus 5% ohm. This is the third option. Okay, yes. The next question, which among the following statements is correct? 1. In a metal, number density is independent of temperature. That is true. In a metal, the electron number density is not going to be varying according to temperature in a metal. But this is not the case in the case of semiconductors and insulators. The second statement, with increase in temperature, relaxation time in metal decreases. That is also true. When temperature is increased, there will be faster movement for the electrons. Faster movement means in a collision in a faster rate means the relaxation time is reduced. Relaxation time is reduced. Okay. Then third one, for semiconductors and insulators, number density increases with increase in temperature. That is why in the case of semiconductors, when temperature increases, conductivity also increases. Okay, that's the reason. Okay, in semiconductors, when temperature increasing, the conductivity also increasing. We studied it. Why? Because there is increase in the number density of the charge carriers. That's why. So all above statements are correct. So our answer is option D. Okay? Yes. Moving to the next question. Nichrome has resistance of 75.3 ohm at 30 degrees C. Okay, at a temperature T1 is represented as 30 degrees Celsius. The resistance of the nichrome wire is 75.3 ohm. Good. The resistance of nichrome becomes 85.8 ohm when current passes through it. When current passes through it means its temperature is increasing. Temperature is increasing. If average temperature coefficient of resistance of nichrome is 1.7 into 10 power minus 4 degrees Celsius inverse. Okay, degrees inverse, right. Alpha, the temperature coefficient of the nichrome wire is given in the question as 1.7 into 10 power minus 4 degrees Celsius inverse. The temperature of nichrome now is, after passing the current, the resistance has increased and the new resistance R2 is given in the question as 85.82 ohm. Clear? Okay. Then what is the new temperature T2 is asked? Clear? We have the relation between the resistance and temperature of a conducting wire as R is equal to R0 into 1 plus alpha into T. This is the formula. Okay, where R0 is the resistance at 0 degrees. R is the resistance at T degrees. R0 is the resistance at 0 degrees. Okay, actually here this is T minus 0. That is simply T. Okay. R0 is a resistance at 0 degrees and R is a resistance at T degrees Celsius. Alpha is the temperature coefficient of the material of the wire. Okay, based on this equation we form two formulas. One is R1 is equal to R0 into 1 plus alpha into T1. Then R2 is equal to R0 into 1 plus alpha T2. Okay, dividing, we get R0 get cancelled. Okay, R2 divided by R1 is equal to 1 plus alpha T2 by 1 plus alpha T1. Here alpha is given, T2 is asked, T1, R2, R1 are given datas. Okay, R2 is 85.8. 85.8 divided by 75.3. Okay, is equal to 1 plus alpha into T2 divided by 1 plus alpha into 30. Okay, here the temperature is in degree Celsius unit. Okay, here we can divide this and it is almost 1.14 in that range, 1.14. Okay, this data is in 1.14, you can check it. 1.14 in that range, you can check it. I'm not doing this now, it's just a wastage of time, you can easily do this one. Okay, then this is almost this value. Okay, now this 1 plus alpha into T2 divided by 1 plus 30 alpha. Okay, now we can solve it. We can solve it. How we solve it? See, I may solve here. 1.14 plus 30 into 1.14 alpha is equal to 1 plus alpha T2. Can I write this here? 1.14 plus 30 alpha into 1.14 is equal to 1 plus alpha into T2. Clear? Then this one to this side we get 0.14. 0.14. Okay, this one to this side, and this 30 alpha into 1.14 to that side. Okay, we get this is alpha is common. In the bracket we get T2 minus 30 into 1.14. 30 into 1.14. 30 into 1.14. Clear? Now this T2 is equal to, see, T2 is equal to, we write this 0.14 divided by alpha plus 30 into 1.14. Simple calculation. The alpha is given here. Alpha value is 1.7 into 10 raised to minus 4. Okay. Okay. This will be around 820. Okay. 830, 820 in that range. And this is 20 to 30 range. Sorry. This is more than 30. 30 into 1.14. Okay. Okay. 33 or in that range. This is around 820. So our answer will be 850 degrees Celsius. The calculation is very simple. You can easily do that. Just remember how we solved this. What is the formula? Okay, that's all. I hope you understood it clearly. Moving to the next question. Number 10th. Listen. The incorrect statement among the following statements is incorrect statement. Option A. EMF of a cell is the potential difference between its positive and negative electrodes in an open circuit. That is true. That is the definition of the EMF itself. What is the EMF of a cell? That is the potential difference between the electrodes if it is not connected to an external circuit. If it is not connected to external circuit, then there will be a potential difference. Okay, one electrode is at higher and the other one is at lower potential. So definitely there is a difference in the potential. That is EMF. And if we connect the cell to a resistor, then there is a potential difference across the resistor. That is V. That is V, and we have expression V is equal to E minus IR. We studied it. Okay. So the first statement is the correct statement only. Now second. Internal resistance of dry cells is much higher than common electrolytic cells. It is a fact. It is also true. Generally, dry cells are having greater internal resistance. Okay. Third, the terminal potential difference of a cell can be 0. The potential difference of a cell can be 0. Potential difference can be 0. It is possible. Potential difference, that is, the cell is not providing any potential difference and it became useless. Okay. And when current passes from positive to negative terminal of a cell inside it, terminal potential difference is less than its EMF. Okay. This is to be carefully listened. We are representing a cell. Okay. And as per the fourth option, they are saying that the current is passing from positive to negative terminal inside the cell. Inside the cell, this is that region. Inside the cell, this is that region. And the current is passing from positive to negative terminal. So the flow of current is in this way. Flow of current is in this way. Okay. Now what is happening to the cell? Now the cell is getting charged. It is not being discharged. It is being charged. Okay. Usually when we connect a cell to a resistor, listen. When we connect a cell to a resistor, the current flow from positive terminal to negative terminal outside the cell and from negative to positive inside the cell. Okay, this is usually happening and this cell is now getting discharged. It is being discharged. Okay, in this context, what is the connection between the potential difference and EMF is V is equal to E minus IR. E minus IR. Okay, now in this situation, actually we are connecting this cell with another cell. We are connecting this cell with another cell. See, another cell. Now this cell has greater EMF. Suppose this cell has greater EMF. This cell has greater. Suppose here is a resistor also connected. R. Okay. A resistor is connected here. Okay. This cell has greater EMF. Then this is being discharged and this is being charged. Okay. In this context, this is having greater EMF. That's why it sends current from positive to negative. This cell sends current from positive to negative because it is having greater EMF. Now, in this cell, the current is from positive to negative within the cell. So this is getting charged. In this context, the potential difference of this cell is E plus IR. E plus IR for this cell. Okay. Understood clearly? Yes. Now what about the statement? In this context, they are saying that potential difference is less than the EMF. Is it true? The potential difference is more than the EMF. IR to be added with EMF. Okay. So this statement is incorrect and that is the answer of the question. Okay, good. Moving to the next question. 11th. When a current of 2 ampere flows in a battery from its negative to positive terminal. Okay. When a current of 2 ampere flows in a battery. Okay. From its negative to positive terminal, the potential difference across it is 12 volt. If a current of 3 ampere is flowing in opposite direction, it produces a potential difference of 15 volt. The EMF of the battery is dash. Here the current is flowing in a battery, means inside the battery. Okay. So there are two situations for a battery, and the current is flowing from in a battery. In the first case, from its negative to positive. From its negative to positive. In a battery. Okay. In this situation, what is V is equal to E minus IR. V is equal to E minus IR. Okay. And the second situation, in the second situation for the same cell. For the same cell in the second situation, the current is flowing in the opposite direction, means from positive to negative in the battery. Okay. In this situation. Okay. This is being charged and this is being discharged. In this situation, what is V is equal to E plus IR. Understood? E plus IR. Okay. Now, in this case, current is 2 ampere and potential difference is 12 volt. Here, in this case, the first equation is 12 is equal to E minus I is 2R. Equation number 1. The second situation, in this case, 15 is equal to E plus, now the current is 3. Current is 3 ampere in the second situation, 3R. Clear? Yes. We got 2 equations, very linear equations. Now what to be calculated? The EMF of the battery is. EMF is to be calculated. So we can eliminate this internal resistance. So this equation is multiplied with 3. This equation is multiplied with 3. We get 36 is equal to 3E minus 6R. Okay. And the second equation is multiplied with 2. This is multiplied with 2. We get 30 is equal to 2E plus 6R. Now these two equations are added. We get 66 is equal to 5E. Yes. 66 is equal to 5E. Okay. Now what about the EMF is E is equal to 66 divided by 5. 66 divided by 5 is 13.2. 13.2 volt is the answer, right? 13.2 volt is the answer, is option D. Okay. Yes. Clear? Yes. Moving to the next question. In the combination of two cells in parallel by joining positive terminals together and similarly two negative ones, okay, the value of E equivalent by R equivalent in the circuit is combination of cells. We studied the theory of combination of cells. Okay, parallel and series. In the figure, two cells are combined in parallel. Okay, now the resistance, the internal resistance is mentioned here like this. Internal resistance mentioned. Okay, this combination is connected to an external load. External load R. Okay, yes, this is the situation. This is having EMF E1, internal resistance R1. Second one having EMF E2, internal resistance R2. Clear? Then we have derived the equation of E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. Very direct. Equivalent by R equivalent is equal to E1 by R1 plus E2 by R2, very direct. E1 here in the question is 8. 8 by 2, that is R1, plus 6 by 2. Okay, 4 plus 3, that is 7. Okay, and voltage by resistance is ampere, that is the unit of E equivalent by R equivalent. Voltage divided by resistance, that is ampere. So it is 7 ampere. The first option is the correct answer. Clear? Okay, combination of cells. Okay, if they are connected in series, what happens? Equivalent is E1 plus E2 plus E3 plus etc. And R equivalent is R1 plus R2 plus R3 plus etc. When they are connected in series. Okay, yes, studied it. Moving to the next question. When a metal conductor connected to right gap of a meter bridge is heated, the balancing point from left end is, okay, what happens? It is heated. It is heated means its resistance increases. Clear? We are having a meter bridge like this. Here is a gap. This is the left gap. Here is another gap, the right gap. Okay. Here there is a wire of 1 meter length. 1 meter length wire. Okay. Here we connect the primary circuit. Okay. Connect the primary circuit. Okay. Okay. This is the connection of the battery. And here we are having a standard resistance. Let it be R. And here we are connecting a wire whose resistance to be measured. Let it be S. Okay. Here we are having a galvanometer connected to a jockey and pressing here J. Let this point be A and this point be B. Yes. This is the picture of meter bridge. Isn't it? Yes. Let this length be L1 from A to J and then this length be L2. Then we are having the equation at balancing that R by L1 is equal to S by L2. This is our formula. R by L1 is equal to S by L2. Okay, balanced Wheatstone bridge formula. P by Q is equal to R by S in that way. Okay, this resistance by resistance of this wire is equal to this resistance by resistance of the remaining wire. That's it. Okay. Now, actually here length, here there will be a resistance per unit length here also and will be cancelled. You studied it, no problem. Now here what is saying that a metal conductor connected to the right gap is heated. Means S value is increasing. Okay, S is being increased. Yes, S is increased. What happens? S is increased, then what happens? See, we have S increasing. We have R is equal to, R is equal to, I write S into L1 by L2. Okay. Now see, R is the constant. R no change for R. This resistance is fixed. This is the constant, means this is a constant. This is a constant means when S increasing, this quantity to be decreased. Yes. Okay. Here, while heating, S is increasing. Then L1 by L2 to be decreased. L1 by L2, when it will be decreased? It will be decreased when L1 is decreasing. L1 decreasing means automatically L2 increasing. Okay. Okay, no problem. L1 decreasing, L2 increasing. So this quantity remains constant because S is increasing. S increasing. So this should be decreasing. L1 decreasing and L2 increasing. Now what are the options? The balancing point from left end. This L1 decreasing means this balancing point is shifting towards left. Yes. Yes. Balancing point is shifting towards left. Shifts towards left. The first option is the correct answer. Shift towards right, incorrect. Remains unchanged, incorrect. First shift to right and then to left, incorrect. Understood? Okay? Yes. The next one. Resistance P, Q, S and R are arranged in clockwise cyclic order to form a balanced Wheatstone bridge. Okay. The ratio of electric power consumed in the branches P plus Q and R plus S is. Power ratio is asked. Okay. We are having a balanced V-stone bridge. Resistances. There are 4 resistances. Okay. These are the 4 resistances. Okay. Here is the galvanometer connected. Okay. Here is the cell is connected. Okay. In the cyclic clockwise order P, Q, S, R. P, Q, S, R. P, Q, S, R. Okay. When it is balanced, there won't be current between these 2 points. Okay. In this arm, no current will be there. So that's why I'm not drawing that. Okay. This is ineffective. No current through it. Okay. Then P and Q are in series. R and S are also in series. And balanced condition is that. What is the balanced condition? Balanced condition is that P by Q is equal to R by S. P by Q is equal to R by S, or P by R is equal to Q by S, or S by R is equal to Q by P. Okay, in any manner we can say, no problem. This is the balanced condition. Okay. Now the question asked is regarding the ratio of power across P plus Q. This is in series combination. So power consumed across P plus Q to the power consumed across R plus S is asked. See, between these 2 points, potential difference will be fixed. Okay, so the potential difference applied across P plus Q and R plus S are same. Okay. Then we are writing the equation of power consumed by a resistor in the form of potential difference. Okay. We have power consumed is I square R is there, V into I is there, and V square by R is there, V square by R. Okay. Okay, in this format it will be useful because potential difference across the point is same for both combination, for this and this. Okay, then the power across P plus Q divided by power across R plus S. Since this potential difference is same, this power is inversely proportional to resistance. Okay, then this ratio will be R plus S divided by P plus Q. Okay, you know these resistors are connected in series, that's why the equivalent resistance will be the sum. And this power is inversely proportional to resistance, then this power ratio will be the resistance in this case, that is R plus S divided by P plus Q. Okay. Now what to do? Now what to do? See, we connect this or we convert this R into S and we convert this P into Q. Okay. Then that will be helpful. So here we are having this equation. P by Q is equal to R by S. P by Q is equal to R by S. Let it be a constant. Let it be a constant. Then what is P is equal in terms of Q? What is P is equal in terms of Q is K times of Q. Correct? P is equal to K times of Q. Correct? We place this value here. Okay. And what about R is equal to, look here, R is equal to K times of S. Here. Okay. Now, R is K times of S. Then plus S divided by P is K times of Q plus Q. Okay. Okay. Now, what is common here? Here S is common. 1 plus K is in the bracket divided by, here Q is common, 1 plus K in the bracket, 1 plus K cancelled, and this is S by Q, S by Q. This power ratio is equal to S by Q. Power ratio is equal to S by Q. Look into the options S by Q. No. Here is Q by S is here. No S by Q. Then what to do? Then S by Q check. What is S by Q? What is S by Q is R by P. Look into this equation. Into this equation, S by Q is equal to R by P. R by P and R by P is here. The answer is option 2. Clear? Understood? Clearly? Okay. The next question is, a battery of EMF 5 volt and negligible internal resistance. Here, this is the battery. You can see 5 volt. Okay, internal resistance is neglected, very small value. Is connected across the diagonally opposite corners of a cubical network consisting of 12 resistors. A cubical network which has 12 sides. Okay, each sides are having resistance. Each of resistance 1 ohm given in the question. Each resistor values 1 ohm. The current along one edge of the cube is. Okay. Actually here in the figure mentioned I and it is asked in the question. Along one edge. See, here the current is splitting at this junction. See, listen. At this junction, this current I is splitting into I by 2 and I by 2. I by 2 and I by 2. Here the current will be I by 2 and in this resistor the current will be I by 2. Okay. And you can see this current I at this junction, it splits into I by 2, I by 2. I by 2 joins here forming I. That is the way. Okay, I think you understood it. So here in the figure mentioned at this junction current is splitted into 3 and the values are mentioned as I. But here it is I by 2, here it is I by 2. Okay, but here it joins as I. Okay, then here in this arm it will be I by 2, in this arm it will be I by 2, in this arm it will be I by 2, in this arm it will be I by 2. Okay, and current along one edge is asked. One edge means in different edges different current. Okay, there is I across certain edges and I by 2 across certain edges. So what we calculate here is I. Otherwise the question to be completed like the current across AB or across BC in that way. Across AB it is I and we are going to calculate I. How much is I? Okay, yes. See, we are moving or we are following Kirchhoff's loop rule. That is the easiest one here to apply. Kirchhoff's loop rule. Kirchhoff's loop rule is an important, highly useful formula. How we apply this? We studied the statement that the algebraic sum of the changes in potential across a closed loop will be 0. Okay. Then we can move in another way. Listen me. Suppose here is a cell. Clear. And a resistor. Clear. Okay, let this be having V, potential difference, okay, and it's having resistance R, okay. Then we start from this point A, moving in this direction, and let this point be B, okay. Now we are having Ohm's law as, listen me, we are having Ohm's law as V is equal to IR, V is equal to IR, okay. Let I be the current flowing through the resistor. I be the current flowing through the resistor, V is equal to IR. That is Ohm's law. This is Ohm's law. Okay. Now, can we apply Kirchhoff's loop rule to this one? Yes. It's very simple and we will get this formula. Kirchhoff's loop rule is the general one. We cannot apply Ohm's law into all situations, but we can apply Kirchhoff's loop rule into many network situations to solve them easily. Okay, then how we apply Kirchhoff's loop rule here is, suppose I am starting from this point. Listen carefully. I am starting from this point. Then I write VA. The potential at A is VA. And now I am moving along the current. And I am crossing this resistor. While we cross the resistor along the current, the potential difference is negative and the difference value is IR. Okay, in the direction of current. Why? Because we are moving along the current and we are just checking the potential difference across this resistor. The difference in potential means final potential minus initial potential. Look into my hand or look into the marker. Okay, listen. Final potential minus initial potential. See, the potential here is less compared to the potential here. That's why the current is moving in this direction from higher potential to lower potential. So this potential difference will be negative. Understood? And the amount of difference is IR. Okay, and we reached here, and we reached to the point B. We reached to the point B. So this I am writing is equal to potential at B. Started from A, so we started VA, then minus IR, and we reached to the point B. So we have written is equal to VB. Okay. Now this term to that side, that term to this side, we get VA minus VB. VA minus VB is equal to IR. Okay. And what is VA minus VB? That is the potential difference of the battery. That is V. This is V. V is equal to IR. V is equal to IR. Okay. Yes. We can proceed in the same manner here. We start from A. Suppose we are moving along B and in this direction and in this direction and starting this point. Okay. Yes. Let this point be D. Suppose this point be D. Okay. Now look here. I'm starting from here. So VA. Now I'm moving in this way. And here each arm there is resistor. Okay. In the question mentioned, in each arm there is resistor. Okay. And the current is moving along the resistor. So the potential difference is minus IR there. Okay. And at this junction current splits into two. I by 2, I by 2. You understood? I by 2, I by 2. So we are moving in this direction. So here minus I by 2 into R. Now we reached here. Now here in this arm it is I itself minus IR. Now where we reached? We reached up to the point D, and that is equal to the potential at D. Clear? Okay. Now VD to this side and all these terms are to that side. We get VA minus VD. VA minus VD is equal to IR plus IR plus I by 2R plus IR. Understood? Yes. Then what is VA minus VD? VA minus VD is the applied potential difference 5 volt. 5 is equal to IR plus IR by 2 is 3 IR by 2 plus IR is 5 IR by 2. 5 IR by 2. 5 cancelled and IR is equal to 2. And R is given in the question as 1 ohm. So what is the value of I is equal to 2 ampere? You understood? I is equal to 2 ampere. Very easy. Okay. And then I by 2 will be 1 ampere. Definitely. Okay. If in the question they are asking what is the current across PQ, suppose PQ, then our answer is 1 ampere. Okay. Understood? Yes. The next question is 16th one. 4 arms of Wheatstone bridge have the following resistances. AB is 60, BC is 100, CD is 60, DA is 12. A galvanometer of 15 ohm is connected across BD. Okay. Calculate the value of additional resistance connected across CD to balance the bridge. What is the meaning of balancing the bridge? Balancing the bridge means there won't be any current across the arm BD and the galvanometer shows 0 deflection. Okay, that is a condition of balancing. Clear? Yes. Let it be P, let it be Q, let it be R, let it be S. Okay. Okay. Then after balancing, let it be P, then Q, then R, then S. Okay. After balancing. See, in this network given in the question, this is not balanced because 60 by 12 is not equal to 100 by 60. It is not balanced. 60 by 12 is 5. 100 by 60 is not equal to 5. So this network is not balanced. So we have to do something. We have to connect some resistance somewhere, some value. And they are asking how much resistance to be connected across CD. So after balancing, I am writing P by R is equal to Q by S. Q by S. Clear? Yes. Then this P is no change in P value, that is 60. No change in R value, that is 12. And Q value is here 100. And S value we have to calculate first. S value we have to calculate first. Okay. 60 by 12 is 5 is equal to 100 by S. Okay. Then what should be the value here for balancing? That is S is equal to 100 by 5, that is equal to 20 ohm. Okay. So the equivalent resistance in the arm CD to be 20 ohm. 20 ohm. At present the resistance here is 60 ohm. Okay. In order to reduce the resistance here, what we need to? We have to connect some resistances in parallel with 60 ohm. Okay, we have to connect some resistance, some resistor in parallel. Then only this equivalent resistance here will be reduced to 20. Okay, and how much is to be connected? That is the question. How much resistance to be connected? Suppose we are connecting resistance S dash in parallel with the 60, then what will be the equivalent resistance? The equivalent resistance of parallel combination is R1 R2 divided by R1 plus R2. Okay, then here is 60 into S dash divided by 60 plus S dash is equal to, and this is the equivalent resistance, and that equivalent resistance is to be 20 here, 20, then only it will be balanced. So this is equal to 20. Good. 20, 60 cancelled, here 1, here 3. So we get 3 S dash is equal to 60 plus S dash. Very simple. Then S dash to this side, 2 S dash is equal to 60. S dash is equal to 30 ohm, right? 30 ohm. Yes. So how much resistance to be connected across CD? Across CD we have to connect 30 ohm. That should be in parallel with 60. Across CD means that will be parallel. Here we are connecting like this. Like this. Then it will be parallel to 60. 30 ohm to be connected here. Then the equivalent resistance will be 20 ohm there, and the network will be balanced one. Okay. Clear? Yes. The next one. In a meter bridge, null point is found to be at 30 centimeter from NDA. From NDA, the null point is at 30 centimeter. If now a resistance of 10 ohm is connected in parallel with S, here in parallel with S we are connecting 10 ohm, the null point occurs at 65 centimeter from NDA. Okay. Value of S is nearly, then what will be the value of S? Okay. Yes. Now, before connecting 10 ohm, means in this situation, we write R divided by L1. L1 is given in the question as what? 30 centimeter. Okay, without connecting 10 ohm, as it is as shown here. This balancing length is 30 centimeter, then this will be 70 centimeter because the overall length is 1 meter, means 100 centimeter. So R divided by 30 is equal to S divided by 70. This is one equation. 0, 0 cancelled. 0, 0 cancelled. Okay. We are having S is equal to one equation. S is equal to 7 by 3 of R. One equation is obtained. Yes. Now, what they have did? They connected 10 ohm in parallel with S. In parallel with S. Then the balancing point shift, the balancing length is 65. Then we get R divided by 65 is equal to S dash. I am writing S dash. The new resistance here is S dash divided by 35. If this is 65, then the remaining will be 35. Total is 100. Okay. Understood? Yes. Okay. Better we take here R is equal to. That's better. And here also R will be getting, and we are equating that. Here R is equal to 3S by 7. That's better. Okay. This equation. Now here what about R here is equal to 65 by 35. We can divide these two with 5. Here it comes 13. Here it is 7. 13 by 7 into S dash. Here R is 3 by 7 into S. Here R is 13 by 7 into S dash. Equating these two, we get 3S by 7 is equal to 13S dash by 7. Okay, 7 cancelled. Okay, then S is equal to, the value of S is asked, S is equal to 13 by 3 into S dash. Okay, 13 by 3 into what is S dash? S dash is the new resistance here. After connecting 10 ohm parallelly with S, then what will be the equivalent resistance is? After connecting 10 ohm, R1 R2 divided by R1 plus R2. That is 10S divided by 10 plus S. Here is S. Okay, this S is cancelled. Okay, then 3 into 10 plus S. 3 into 10 plus S is equal to 130. 30 plus 3S. 3 into 10, 30 plus 3S is equal to 130. Clear? Yes. 3S is equal to 100. Yes. Simply. 3S is equal to 3S is equal to 100. S is equal to 100 divided by 3. It is 33.33. 33.33. So the answer is nearly 33 ohm. Answer is option C. Look into the steps, very easily done. Okay, good. The next question. In a potentiometer of 8 wires, the balance point is obtained on 5th wire. To shift balance point to 6th wire, what we should do? This is the question. Potentiometer. See, point A, wire 1, 2, 3, 4, 5, 6, 7, 8. This is point B. Okay. Here is a primary circuit, primary cell. Okay. Connected here. This is the primary circuit. Okay. Here is a secondary circuit. Okay, galvanometer, choke. 1, 2, 3, 4, 5. It was on 5. So this is the secondary circuit. Okay. Now, what is the concept? Suppose this key is, suppose here is a key. Okay. Yes. Like this. Okay. Now, suppose this is open. Now the primary circuit only connected between A and B. Okay. Then here is a potential difference applied across this much wire. Okay. Listen carefully. A potential difference applied across this much wire. Okay. For example, across 8 meter wire, suppose 8 volt potential difference is applied here. For example, listen. For example, across 8 meter wire, a potential difference of 8 volt is applied. Then my question is, how much will be the potential difference across 1 meter? Across 1 meter, the potential difference will be 1 volt. Okay. Yes. Suppose we are closing this circuit and the jockey is pressed here. Okay. At a length of 5.5 meter. 5.5 meter, 5.5 meter suppose, and the galvanometer shows no deflection, which means, what does it mean? It means that here, the total potential difference of the cell and this resistor is the potential difference corresponding to 5.5 meter. How much is the potential difference corresponding to 1 meter? As per this is 1 volt. Then what will be the potential difference corresponding to 5.5 meter? It will be 5.5 volt. 5.5 volt. If this resistor is not here, then what will be the EMF of this cell? The EMF of this cell will be the potential difference corresponding to 5.5 meter. That will be 5.5 volt. Balanced. That's why galvanometer shows zero deflection. This is the concept. Okay. Suppose here we are increasing the voltage of this cell. See. We are increasing the voltage of this cell. What will happen? The potential difference per unit length of the wire will be increasing. That will be increasing. Then to balance the EMF of this cell, we require only lesser length. You understood? Carefully listen. If we increase the EMF, for example 8 volt, we increase it to 16 volt, then what will be the volt per meter value will be 2 volt. So across 1 meter there will be 2 volt. So in order to balance 5.5 volt of this cell, we only require a less length, not 5.5 meter required, because each and every meter having 2 volt now. I think you understood it. Okay. In that way we have to think. If we are increasing the resistance value here, okay, then what happens? Increasing the resistance value here means the potential difference per unit length of this wire is decreased. This wire decreased means to balance this cell, we require more length. Potential difference per unit length is decreased if we increase this resistance. Then potential difference across this cell increases. Then potential difference across this entire wire decreasing. Then we require more length to balance it. I think you understood the concept. Yes. Now in this question, earlier the balancing point was on the 5th wire. Now to shift the balancing point to the 6th wire, what we need to do is asked. Option A, decrease resistance in main circuit. This is the main circuit. This is the resistance. If we decrease the resistance in the main circuit, what will happen? The potential difference across this entire wire increases. Potential difference across this entire wire increases means we require only less length to balance this cell. Less length only. Then from 5th wire to 4th wire or 3rd wire it will be shifting, not to 6th. You understood? Here we are decreasing this resistance. So potential difference across this is reduced. Then across this will be increased because overall we are applying this total potential difference. Understood? Understood. Suppose this is 16 volt. Okay. Across this 6 volt. Then across the wire 10 volt. Okay. If we increase the resistance, then across this 8 volt. Then across this 8 volt. Okay. If we decrease the resistance, then across this potential difference is decreased. Then across this will be increased. This across this will be increased means we require only less length. So decreasing resistance is not the answer. I think you understood. Then increase the resistance in main driver circuit is the answer because these two statements are contradictory. Then one will be the answer definitely if there is a possibility. Okay. Increasing resistance here means decreasing the potential difference here. Then to balance this voltage we require more length. I think you understood the concept of potentiometer. Our answer is this one. What about the other options? Increase resistance in series with the cell whose EMF is to be measured. This cell whose EMF is to be measured and there is a resistors in series. If we are increasing the resistance here, then we require only very less length to balance. Very less length to balance. Okay, then it is not shifting to 6th. Okay, so this is not correct. Taking driver battery with higher EMF. Driver battery with higher EMF. Then what happens? Here voltage per unit length will be increasing. Here voltage per unit length will be increasing means less length only we require to balance this. I think you understood the concept of potentiometer now. An important one. Okay? Yes. Moving to the next question. 19th. A potentiometer again with a driver battery of EMF 2 volt is used for determination of internal resistance of 1.5 volt cell. Okay. Okay. Potentiometer, primary circuit. Okay, and here we connect a cell whose EMF is to be connected. Galvanometer, jockey stick. Okay, here we connect a resistance box with a key. Okay, initially the key is open. Now the cell only included in the circuit. And we are having a balancing length L1. Then by the formula we are having the EMF of this cell is equal to some constant phi into L1. Understood? And this constant phi is, as I mentioned in the earlier question, this is the volt per meter value. Volt per meter value into length is the EMF. Okay, that is here in the open circuit. See, used for determination of internal resistance of 1.5 volt cell, the balancing point of the cell in the open circuit is 225 centimeter. So this L1 value is 225 centimeter. Now, when this key is closed, a resistance of 7 ohm is used in the external circuit here. The balancing point shifts to 210 centimeter. When this resistor is included, then we are having the potential difference across this point, not EMF. Potential difference. In that case, we are having V is equal to phi into L2. Yes. Okay, L1 is given 225 cm, L2 is given 210 centimeter, EMF is given 1.5 volt. Okay, the resistance connected is given 7 ohm. Okay, what is to be calculated? The internal resistance of the cell is asked, internal resistance. Just divide these two, E by V is equal to L1 by L2. Okay. Okay, and we are having the formula V is equal to IR, where R is this external resistance connected, and EMF is equal to I into R plus R. This is the formula. Okay, how we get this? This we get V is equal to E minus IR. Okay, you know that formula? V is equal to E minus IR. Okay, then what is E is equal to V plus IR? E is equal to V plus IR, and V is IR. So IR plus IR. Okay, it's familiar. Then what is E by V? E by V is this. E by V, I cancelled. Okay, R plus R divided by R is equal to L1 by L2. Yes, 1 plus dividing 1 plus R by R. 1 plus R by R is equal to L1 by L2. R by R is equal to L1 by L2 minus 1. R is equal to R into L1 by L2 minus 1. Yes. This is the equation to find the internal resistance of a cell by using the potentiometer experiment. Clear? This R is 7 ohm, L1 is 225 centimeter, L2 is 210 centimeter. All the values are given. Very direct. Okay, we need to calculate the internal resistance of the cell. We can calculate it here. See. Here. This R is equal to, listen. Capital R is 7, L1 is 225, L2 is 210 minus 1. Okay, 225 minus 210. 225 minus 210 is 15. Divided by 210. Okay, 7 into 15. 7 into 15 is 105, isn't it? Yes, divided by 210. Okay, 105 divided by 210 is 1 by 2. That is 0.5. Yes, 0.5 ohm is the internal resistance of the given cell here. I think you understood very clearly. Okay, yes. The final question is, pick out the wrong statement about the Kirchhoff's laws of electric circuit. Statement 1. Outgoing currents adds up and are equal to incoming currents at a junction. Junction rule. At a junction, the outgoing current, when we add them, will be equal to the incoming current. True. Option B. Electric potential in electric circuit is position dependent. Starting with any point, if we come back to the same point, total potential change must be 0. While applying Kirchhoff's loop rule, potential is position dependent. We are starting from a point. VA minus IR minus I by 2R is equal to VP. In that way. Position dependent. Junction rule is based on conservation of energy law. Incorrect. Junction rule is based on conservation of charge law. Conservation of charge. How much charge entering, that much charge will be leaving. That's the current entering will be the current leaving. So this will be our answer. Incorrect statement only to select. Okay, wrong. That is the answer C. Bending or reorienting the wire does not change the validity of Kirchhoff's junction rule is true. Okay, electric current is not a vector. Okay. We bend like this, the same current flows as it is. No problem. So the answer is option C. I hope you understood all the questions very clearly, very thoroughly. Okay. Keep up the good work, study well. See you again. Thank you.